This is EC 201, lecture 39. So far in this course, we have seen how to analyze nonlinear networks in the small signal sense, which is you to take a nonlinear element and perturb the applied voltages and currents. You can relate the increments in the voltages and currents by a bunch of linear equations, which basically reduces to a linear incremental equivalent network. And we've always assumed that there are no memory effects inside the nonlinear devices. In other words, if you took a nonlinear device, we've always assumed that I is some nonlinear function of the applied voltage. Do you think there is some limitation with respect to this, or should this be sufficient to describe all varieties of nonlinear one-ports? In the realm of linear networks, this question would be analogous to, if you had a linear one port, is just a resistor enough to describe it, or do you need something else? Are resistors enough to describe all classes of linear networks? Clearly, when you have linear electrical networks, the resistor case is just sufficient to take care of those networks without any memory or energy storage. The moment a linear network has memory, then you need at least one set of reactive elements, either the capacitors or inductors or both, or in general you need transmission lines. These are all classes of linear elements with memory. So in general, the same thing holds for the nonlinear case also. Any network can in principle be both nonlinear and have memory. So the describing equations, which were all in the memoryless case were all just nonlinear equations, now become the equations describing the operation of a linear network with memory. What kinds of equations are they? They are all linear differential equations. So it follows that if you have a nonlinear device with memory, the governing equations will all be sets of nonlinear differential equations, and it's hard enough to solve nonlinear algebraic equations, and we've already figured out how to do it in a restricted sense where we only deal with increments. So you can only imagine how complicated dealing with nonlinear differential equations is. So we follow the same trick that we have used before, which is we don't worry about trying to solve these sets of nonlinear differential equations for all possible inputs. We only address the issue where the signals to the network are all incremental signals around an operating point. So if you have a set of nonlinear algebraic equations describing the operation of a network, for incremental signals, what do you get? A linear network with resistors and controlled sources, etc. But the key point is to note that there is no memory at all. Now, if you have a network described by nonlinear differential equations, what can you expect to get for incremental signals? In the first case, when we had nonlinear algebraic equations, for incremental signals you would get linear algebraic equations. When you have nonlinear differential equations describing the device or the network, for incremental signals you will expect a set of linear differential equations, which means that the incremental equivalent circuit consists of what? It will consist of linear elements with memory. examples L's, C's, etc., transmission lines, etc., can all appear now in the incremental equivalent circuit. So again we have reduced the problem of a very complicated beast to something tractable, because we have spent a lot of time trying to figure out how linear circuits work. So within the realm of incremental operation, we can see that we now, instead of having to solve a resistive network, we have to solve a network with inductors, capacitors, resistors and so on, and this needn't bother us because we are used to doing this. And you can use all the standard tools of linear circuit theory, which are all the transform tools, right? Laplace transforms, Fourier transforms, I mean everything that holds with linear system with memory can also be used here. So all that we have learned in networks and systems just becomes directly applicable to a nonlinear network also, provided the excitations are all small c. Without getting into the details, I will just put down the equivalent circuit of the MOSFET operating in saturation. We said that the incremental circuit of the transistor was this. So this is the gate, this is the source, this is the drain, gate, drain, source. This is what we had earlier. The incremental voltage was VGS. This is GM VGS, where GM is gotten from the formula, and this is RO. Now, it turns out that when memory effects are considered, I mean, you can hardly expect any physical device to react with infinite speed to your input. So, physically speaking, any real system in the world, when you apply an input, it will take some time to respond. The response time can be very, very, very small, but there will always be a finite response time, because when you apply an electrical input, you see a change in the electrical output, and the change in the electrical output is happening because of movement of carriers, and carriers move at finite speed. So it's only logical to expect that changes don't happen immediately. There is always some time required for charges to move. And as technology keeps progressing, devices become smaller and smaller and smaller, which means what? If things become smaller, presumably charge carriers have to move by shorter distances, which presumably means that devices can be expected to get faster, and this equivalent circuit would predict that the MOSFET would respond with infinite speed. So if an incremental VGS was applied, I mean this equivalent circuit would mistakenly indicate that the incremental output current is GM VGS, and that happens right away. In practice, as we would logically expect, there is always finite speed, and when there is inertia of charges moving about, it turns out that you have to actually get into the nonlinear operation of the device, write the nonlinear differential equations, apply a small signal change, and then do what we did for the, I mean, how did we derive this equivalent circuit? We write the nonlinear algebraic equations, add an increment, and then write the new current, then expand it as a Taylor series, subtract, blah blah blah, and come up with the incremental equivalent. You now have to do it with the nonlinear differential equations that govern the operation of the device itself, which is way too complicated for this course. So I will just put down the equivalent circuit, and you take it as space y. As a network theorist, one thing you can be sure is that any two nodes will have capacitance between them. So it turns out that the incremental input impedance of the MOSFET between the gate and source, while it's open circuit for DC, there is a capacitance CGS between gate and source. There is also a capacitance between the drain and gate. So this is CGD, and it turns out the way the MOSFET is constructed, there is a parasitic capacitance between what is called the bulk terminal of the MOSFET. I mean, I basically conned you when I told you that the MOSFET is a 3-terminal device. It's actually a 4-terminal device. Take for granted at this point is that there is always a capacitance from the source to a terminal called the bulk of the transistor. With the bulk of the transistor is always connected to a DC potential, okay, the lowest potential on the chip. And we know that for incremental signals, any DC potential becomes ground. These two represent the so-called bulk terminal of the MOSFET. And for those of you who don't understand this, never mind. As far as the circuit operation is concerned, you can think of adding one capacitance between drain to incremental ground and another capacitance between the source and the incremental ground. It turns out from MOSFET physics that CGS will be much larger than CGD, and CDB, CSB and CGD will be roughly of the same order of magnitude. You can see from this diagram that at very low frequencies, what is the current flowing through these capacitors? These capacitors can all be treated as open circuits and you get back to the original equivalent circuit we saw for DC. And all these are the so-called DC incremental parameters. And what did we say about the incremental parameters? The incremental parameters of the nonlinear device are dependent on the operating point, and by the same token, these are also incremental parameters. By the same token, these incremental parameters will also be dependent on, these also depend on the operating point of the MOSFET. As a network theorist, I can only say that these will be dependent on the operating point. The exact nature of the dependence depends on the details of the device operation, just like the formula for the GM depends on the formula relating I to VGS. So just like that, the values of these are all incremental capacitances, please note, and the values of these incremental capacitances quite logically depend on the operating point of the device, and the exact relation of these capacitances to the operating point of the device depends on the physics of the device itself. And it turns out that this gate source capacitance CGS, for example, is given in the saturation region by 2/3 W times L times COS. Okay, what is W? The width of the MOSFET, L is the length, COS is the oxide capacitance per unit area, and the general unit for COX will be capacitance per meter square type number, and these are in meters, or alternatively if all device dimensions are typically in microns, so COX is often quoted as femtofarad per micron square. W and L are in microns, so you will get CGS is typically quoted in femtofarad type numbers. It depends on the geometry of the MOSFET, and quite serendipitously, so this is true in saturation. So if the MOS transistor is operating in saturation, the incremental gate source capacitance happens to be 2/3 W times L times COX. How this comes about, you will only learn in an advanced device class. And as circuit designers, just like how we didn't really care how the equation for the ID versus VGS came about, we don't really care how these numbers come about, we just care about the numbers themselves. The first thing to do is to figure out what these capacitances do to me. The small signal equivalent to the very first amplifier that we saw was the common source amplifier. Please note that I am omitting all the biasing details because by now you are all quite familiar with it. I also make lambda equal to 0 so that I just deal with one resistor RL. So this was the GM VGS, and for low frequency signals we saw that the incremental gain is minus GM RL. When the frequencies are not low enough, we have to use the complete small signal model for the MOS transistor operating in saturation, and as we have seen, we have to add in or CGD, this is CDB, this is CSB, and this is CGS. Everything in black corresponds to the circuit we had at DC. The extra elements are the ones in red. So obviously, when you try and solve this linear network with memory, you will get linear differential equations. To simplify analysis, you can get into the transform domain, and now we can talk about a small signal transfer function between the output and input, just like what you do with linear networks. All that I have done is replace the old model we were using with the new one. Does CSB influence the performance at all or what? Does CSB matter? In this particular topology, CSB doesn't matter because both ends of the capacitor are connected to incremental ground, which means that the absolute voltage across this capacitor remains constant, which means that no current flows. So we can safely ignore CSB. Now to find the transfer function V out by Vs, how do we go about it? There is no easy way out. You just slog your way through the equations. One simplification might help me. You convert the input source into a Norton equivalent. Not to keep worrying about RS, I will denote 1 over RS as GS. This is VGS. We write Kirchhoff's current law at this node first. What is that giving us? In the transform domain, let me call this Vx instead of having to call it VGS so that I can avoid writing one subscript extra. So Vx times SCGS is the current flowing into CGS. S is the Laplace variable plus Vx minus Vout times SCGD plus GS times Vx must be equal to GS times Vs. The current flowing in this branch plus this branch plus this branch must be equal to the total current coming into this node, and the total current coming into this node is Vs times GS. What about this node? Again, V out times GL plus SCDB. This must be Vx plus V out times V out minus Vx times SCGD. Okay, that's the current flowing out of V out through the CGD capacitor, or plus GMVx must be 0. Is that correct? We have two equations, two variables. Let's now just do the maths. If we want VO by Vs, we should get rid of Vx, so let's do that. So from the first equation, Vx times SCGS plus CGD plus GS must be equal to Vout times SCGD plus Vs times GS. Is that correct? What about the second one? Vout times GL plus SCGD plus CDV must be equal to Vx times SCGD minus Gm. So now all that we need to do is Vout times GL plus S times CGD plus CDB divided by SCGD minus GM must be equal to Vout times SCGD plus Vs times GS divided by S times CGS plus CGD plus GS. Fortunately, there is no clean way of simplifying it. After we do the maths, we will stare at the expressions and figure out what intuition you can gain from the expressions. Okay, we are doing all this math. Let's figure out first what we should expect at least. What do you get a transfer function from input to output. What do you think the order of the network will be? If there were no capacitors, what would be the order? Okay. If there is one capacitor, what will the order be? If there are two capacitors, what can the order be? Can it be 3? If there are two capacitors, can the order be 3? No. If there are two capacitors, can the order be 2? If there are two capacitors, can the order be 1? Can the order be 0? Okay, what is the order of this network? This is Vi, this is Vo. What is the order of the transfer function? C1, let me call this also C1. What is the transfer function? Transfer function is half, the order is 0. How about if I make this R, this C, what is the order? Great. If I do this, what is the order? 2. If I do this, what is the order? 1. So just because you see two capacitors in the network doesn't mean the order is 2. It can be 0, it can be 1, it can be 2. Now, can you tell me what the order of this network is? How many capacitors are there? 3 capacitors. Okay. The order can at most be 3. So can it be 3? It is 3. Okay, let's go and figure it out. So let's do the math now. So V out times this expression minus SCGD divided by S times CGS plus CGD plus GS must be equal to Vs times GS divided by S times CGS plus CGD plus GS. We got to simplify this portion. And that is going to be GL plus S times CGD plus CDB times GS plus S times CGS plus CGD minus S times CGD times S times CGD minus GM. That's the numerator. And the denominator is SCGD minus GM times SCGS plus CGD plus GS. Let's do the math on the numerator. Can you help me here? It's GL GS plus S times GL times CGS plus CGD plus S times GS times CGD plus CDB plus S square times CGD plus CDB times CGS plus CGD minus S times CGD square minus S square times CGD square plus SCGD times GM divided by the denominator. If I expand this, I get CGD CGS plus CGD square plus CDB CGS plus CDB CGD minus, and then this goes away. This cancels with this. I can replace this with S square times CGD CGS plus CDB CGS plus CDB CGD. Alright, and I can move the S term here, and that becomes CGD times GM and this has to be divided by the denominator, which happens to be from the previous page S CGD minus GM times S times CGS plus CGD plus GS. This times V out must be Vs times Gs divided by S times CGS plus CGD plus GS. So let's get rid of the common factor. Which means we are interested in V out by Vs, and that is Gs times SCGD minus Gm divided by S square times CGD CGS plus CDB CGS plus CDB CGD plus S times GL times CGS plus CGD plus GS times CGD plus CDB plus CGD times GM plus GL GS. Before we congratulate ourselves on a job well done, we figure out whether we have screwed up, or first of all, the first thing to check is if everything is dimensionally consistent. The whole thing must be dimensionless. So one thing you can do is to divide throughout by GLGS, so that I will get 1 over GL. This becomes 1. And this is GL GS, and I will divide the numerator also by GM, and take GM outside, so I get GM by GL. I will take the minus outside and do this. So V out by Vs is minus Gm by Gl, which is dimensionless, times 1 minus SCGD divided by Gm divided by the denominator, which strangely happens to be a second order denominator. So what is the order of the system? Second order. The guys who said 3. So is this dimensionally consistent first? Yes. Then what other sanity checks can you make? At DC, what did you expect? When there were no capacitors, we would expect the gain to be minus GMRL, which is the same as saying minus GM by GL. That also happens, because when S becomes 0, this goes away, this goes away, this goes away. That seems fine. The order is 2. There are 2 possibilities. So you could have made a mistake, or the order is truly 2. But you said 3 before. Where were we wrong? stare at this network and tell me why the order is 2. One reason, of course, is we assume that the math is correct and then we get 2, so its order is 2. The number of state variables is 2 because you can't independently assign states to CGD, CGS and CDB. Once you know the voltage across CGS and CDB, the voltage across CGD is automatically fixed. So in other words, the order of the network is the number of capacitors minus the number of capacitor loops. When there is a capacitor loop, all the capacitors in the loop will not be independent. One case in point is here where if it is sufficient to just specify the voltage across this capacitor or this capacitor, and this capacitor to figure out the voltage across CGS. That's why the order is 3 capacitors minus 1, which is for the capacitor loop. So this is a second order system. So that also makes sense. So it's dimensionally consistent. It seems it's correct for DC. Order makes sense. So let's try and get whatever intuition you can glean from this messy looking expression. One thing is to see what happens when CGD becomes 0.